I didn't see you there. You know, calculus is a really useful tool for an engineer. Here, let me show you what it does.
Wow, that's awesome. I love big explosions. But did you know that NASA also used calculus to get a man on the moon?
You're correct, Harris, and we're going to show you how they did it.
Pretend that our friend Cora here is the Earth.
And that Gabby is the moon.
And that Reed over there is the sun.
Now the problem gets even harder. How do we get a rocket from Cora, the Earth, to Gabby, the moon, who is orbiting around Cora, and then Cora, who is orbiting around Reed, the sun, who's hurtling through space at 828,000 kilometers per hour?
Not only that, the Earth has a pesky atmosphere that keeps everybody on it alive. Additionally, we also have to worry about gravity. So, with all of that going on, how do we get the rocket from the Earth to the moon? Let's crunch some numbers.
Let's start by looking at this equation. This equation represents the speed s of an object with mass m in a circular orbit where g is the gravitational constant, m is the mass of an object, and r is its radius. It looks super intimidating, but we can cancel out some of the variables to get.
Then, using this equation, we can plug in numbers that scientists have already calculated, like the mass and gravitational pull of the moon. This means we can figure out the speed needed to take off the surface of the moon and escape its gravity. Now, let's take a look at an example of derivatives in action. If an object is traveling around a circle of radius r in meters at a speed of s meters per second, then its position at the time t in seconds can be modeled by a function such as.
And if we take the derivative of a position function, we get a function that describes velocity. Then if we take the derivative again, we get a function that represents acceleration.
Now we can use s equals the square root of gm over r along with the derivatives we found above in order to calculate the speed and period of an object that's orbiting in a circular motion. This could be used to calculate how to rendezvous in space. The formulas above for speed and period can help astronauts calculate rendezvous in space. For example, if an astronaut was piloting the LMA lunar module Apollo and trying to rendezvous with the CSM command service module, the astronauts on the LMA could use the above equations to help calculate the speed and period of the CSM in order to meet up with it. Look at the function f of x equals 2. Now ignore everything underneath the x-axis. If I were to ask you to find the area of that, you might have trouble because it is a rectangle with a height of 2 but a length of infinity.
Currently, f of x has a domain of negative infinity to infinity. If we were to restrict the infinite domain negative infinity to a finite domain such as 0, 5, then instead of having an infinitely large area, we will have a finite area.
To display the second fundamental theorem of calculus, let's say we have a rectangle from 0 to 5. Using basic geometry, we know the base of the rectangle is 5 units and the height is 2 units. 5 times 2 equals the area of 10 units. But instead of using geometry, we can use an integral to find the area of the rectangle from 0 to 5.
The second theorem of calculus states that the integral from a to b of f of x dx equals fb minus fa, where f is the antiderivative of f of x. The antiderivative from 0 to 5 of 2 dx equals 2x. If y equals 2 is our equation, the antiderivative is 2x. So from 2 times 5 minus 2 times 0, that equals 10. And then we plug in the bounds 5 and 0 and subtract the larger value 5 from the smaller value 0. This gives us an area of 10 units squared. Let's take a break from the equations by looking at the mean value theorem. The MVT explains how for a function f, as long as it is continuous on an interval ab and differentiable on ab, then there is a value c such that f prime of c equals f of b minus f of a all over b minus a.
Well, what does that even mean?
Basically, it means that at some point on the interval from a to b, the slope of the tangent line is equal to the slope of the secant line.
And what does that mean? How does NASA use the mean value theorem?
It means that the average of something must have equaled the slope value in that interval. For example, if NASA was trying to determine the average velocity of an Apollo rocket leaving the Earth's atmosphere and figured it was 11.08 kilometers per second, the rocket would have gone at 11.08 kilometers per second at one point in its ascent. While the speed of a rocket varies all the while it's trying to leave the Earth, the rocket would have hit the total average speed at least once in the interval of the time it took to leave.
Whenever we have more than two bodies in space with a significant amount of mass, we use the nth body problem to model how the bodies might interact with each other. Here's what it looks like.
Whoa, slow down. I hardly understand that. I'm totally lost and my head hurts.
That's understandable. We can't really do it unless we have a computer to simulate all of the variables involved. But to put it in perspective, a real example of a three-body problem is the relationship between the Earth, Moon, and Sun. In this case, while the Moon has gravity, the force that it exerts is negligible, so we call it a restricted three-body problem. Because the Moon is negligible within the system, the whole thing can now be analyzed in terms of a two-body problem, which makes the calculations possible.
Oh, cool. So in this case, the spacecraft is the planetoid with a negligible mass?
That's right, Maddie. And the other two bodies we would use would be the Earth and the Moon. So, when you have Apollo 13 trying to use the gravity of the Moon to slingshot a spacecraft back to the Earth, they used this math.
Hey, didn't NASA use that same idea for the Cassini probe?
Yes! Same concept as the Apollo missions, but just a slightly different execution.
Wow, look at all that math.
Yep, and we hope you learned something.
We hope this video helps you on your math adventure.
Godspeed,
Godspeed, gamers.